Hi guys, welcome to lesson 2 for our online lessons. So I thought I'd start off this time by just giving you a brief recap of the different parts of a wave. So I'd like you to pause the video now and actually attempt to draw a wave and label all the parts. Hopefully you've done that. So what I'm going to do is I'm going to draw the wave for you, and so you can have a look, make sure you haven't missed anything or gotten anything incorrect. So this is our basic wave. Okay, so we'll have some sort of a starting point here. Okay, we'll also have the center line or the rest point. Hopefully yours looks a little bit better than mine, drawing a bit freehand at the moment. Okay, so here, from this point up to here, okay, from rest up to the top, which is the crest, or from the rest point down to the bottom, which is the trough. Okay, this is amplitude. Okay, so a measure of the size of the wave. Okay, next important one to remember, I'm sure you remember this one, no problems, is the wavelength. So usually we measure the wavelength by looking at two successive or two adjacent crests and measuring the distance between them. In this case, we're going to have this one as the wavelength. So remember, we write it as the Greek letter lambda. You can also look at the wavelength by just measuring one complete cycle. So I could start at this point, go all the way over to this point, and so there to there would be one complete wavelength. Absolutely up to you, as long as you're able to accurately measure it. Okay, usually measuring using a ruler, and as you remember, wavelength is measured in meters. Okay. Now, the other important one, I think you're getting these two maybe mixed up sometimes, is frequency. Now, frequency is the number of waves that are passing a point per second. Okay, so in general, we choose, some sort of a starting point. Okay, so if I said up to here, let's say up to this point, that's 1 second. Okay, so in 1 second, okay, how many waves are passing that point? You've got it from going from here, okay, to here. So that's one wavelength. Here to here, two wavelengths. So the frequency in this case is frequency equals how many? 2 wavelengths per second. Now wavelengths, we also call them cycles. 2 cycles per second. And cycles per second is equal to hertz. Okay, and we write hertz as H Z. Okay, now the difference between period, okay, this is the time taken for one full wave to pass. Okay, so that's one complete cycle. This one we're looking at how many cycles are in 1 second. Okay, so in this case, we'd be looking at, say, from this point to this point. Okay, and how many seconds is that? Obviously, you can see that we had 2 wavelengths in 1 second. This is 1 wavelength. It's going to be 0.5 of a second. You can tell straight away. Okay, but the other way to work it out, if it's not quite so obvious, we can do T. That's how we write period. So T is period equals 1 over F. Okay, so in this case, we go 1 over F, which is 2. So that is obviously a half. Okay, nice and easy. All right, so hopefully you've got all that, and that's not going to be any problems for you. What I'd like to move on to is actually working out about waves and boundaries. Okay, so I'm just going to adjust this slightly. Hopefully it'll stay where I want it to stay. Okay, so we're looking at the waves and boundaries now. So basically 2 things can happen, and we were hoping to see this with that experiment we did last week. 2 things can happen when a wave hits a boundary. So you've got a boundary at this side. If it is a fixed, so that's the one we're going to look at first. If it's fixed on this wall, so usually we again use a spring to kind of tell us. So if we've got our little spring or our slinky and it's going up like that and down, okay, and then across. Sorry, it's not very even, but you can get the general idea. This is attached firmly to this wall. It can't move. Okay? Once it hits, so if this wave's traveling along here, when it hits this wall, it does actually reflect back as you'd expect. However, it's going to be actually, well, what we call as a phase reversal or inverted. Okay, so what happens? So if we say this is our wall, we've got our fixed point here. It actually goes back along this way, but it goes like this. Now, this distance here is the same as this one here. Okay, so that hasn't changed at all. It's just become inverted. Okay, so what we actually call that, we call it out of phase, okay, or a phase reversal. So another way they sometimes refer to it, they look at 180 degrees out of phase with the incident pulse, okay, so 180 degrees out of phase. That's basically because of this. I'll draw you a small picture of it. When we have a look at a wave, if it looks like this, okay, we generally say one full wavelength is 360 degrees, okay? Therefore, this one is 180 degrees. As you can see, you've got here is quite different in the separate section to the one down below. So what they're saying is it's basically reflected. It's the way that they use to explain it. Okay, so that's an out of phase one, so that's a reflection. Now if, okay, I might just move this one, I'll turn it over. Hopefully that's okay. If it hasn't got a fixed boundary, so if we've got a different one that actually looks like this, so we've got our wall at the side here, okay, and this is free to move, okay, so it's got some sort of hole there, okay, and it's free to move. What you can actually have is something looking like this. So it goes across, up, down, might go a little bit further down like that, okay, and goes through to the end where it's not fixed. The next thing that could happen, okay, or that probably will happen in this case, is it will move slightly. Now, instead of being reflected inversely, it is going to continue back the way it came from. So I'll give you going across that way. Going to continue back. However, it's going to follow the same pattern. It's going to follow the same pattern as the original one did. So if you can see it there, okay, it's still going to be going up first, then down. As you can see here, up first, then down. So it gets reflected back, okay, exactly. Yep. So hopefully you can see that. That's not out of phase, okay. So we call it in phase. So I'll show you that again. So you've got, I'll write it down for you, out of phase, and then you've got this one here, in phase. Okay. Now, those ones are quite simple. Okay, so hopefully you're able to get that. The difficulties come when it goes through a different medium. So that's again what we were trying to look at with that prac, how we had the heavier spring, we had that slinky attached to the smaller spring. Okay, you should have seen some difference in how it's transmitted. Unfortunately, doesn't always happen, okay? So the pulse actually does still get transmitted into the second spring. So I'll give you an example of how that would look. Okay, so say we've got a lighter spring and then a more dense spring, okay? You're going to have to excuse my drawing. You guys know that I'm not the greatest at that. So you've got less dense spring and you start a pulse on this one. Not good. Here we go, onto the more dense one. Okay, so when it meets this boundary, as you can see here, some of that pulse is transmitted. So we'll see that. Some of it's transmitted. But also some of it's actually reflected. Okay, so transmitted, keeping on going through the different mediums, some of it's reflected and goes back where it comes from. Okay, so basically what we end up getting is something that looks a little bit like this. That is still meant to be the less dense one, I'm afraid. But you will have to just trust me. And then the more dense medium there. Okay, I'm hoping you're going to be able to see that. So what's actually happened is it's hit this boundary, okay, between the two springs. And this one has been reflected. It's gone back where it's come from. So it's kind of like it's hit a wall, okay, in some sense. Now, hopefully you can see that's not just by bad drawing, but this one, okay, the amplitude is actually less. I have intentionally drawn it that way. So the amplitude is a little bit less. It goes back this way. Some of it is being transmitted, and you'll see that it's still in phase. Okay, so that one's going up. It's still in phase. This one behaving like a fixed boundary. Okay, and it's getting inverted as it goes back. Okay, so it's out of phase. So you've got out of phase. And then this one going this way, it's in phase. So the one that's transmitted is in phase. Okay, so that's if it's going from a lighter spring, less dense spring, to a heavier spring. Now the other one we can look at is the other way around, obviously. Okay, so the next one is going from a heavier to a lighter spring. So again, we start off with my beautiful drawing. So this is your more dense one, going up. Going down again, skews the writing. Okay, so it goes to here, and then it goes into the less dense spring. Okay, now the pulse is traveling in this direction. So again, it's going to act as though it's hit some sort of a wall. Okay, so what actually happens, because it's going to a less dense one, okay, it behaves like it's a non-fixed boundary. So when it gets reflected, okay, so remember the two things are going to happen. You're going to get some reflection and you're going to get some transmission. So some of the wave's going to be transmitted, some of it's going to be reflected back. When it gets reflected back, what you're actually seeing happening, maybe I should start it from this point, it actually goes back along. Oh gosh, that's worse and worse. Okay, and goes along. Again, the amplitude's less, but you're going to see it's in phase. Going from a heavier to a lighter, okay, when it gets reflected back, it does stay in phase. Okay, this one on the other hand, okay, it continues on that way, and it does just get transmitted in the same direction or the same amplitude in phase with the original wave. Okay, so that's the same as what happened before. So this is in phase too. Okay, so that's going that way and then reflected back that way. Now, you'll see this. So things like, you know how water travels better, sound travels better in water than it does in air. Okay, and light travels better in a vacuum than it does going through glass and things like that. This is where that really is illustrated. So that's what happens. Because it's going through a different medium, different things can happen to those waves. Now, so this is just fairly basic, okay? So we're just looking at reflection for the moment. The next one we're going to do is we're actually going to look at superposition, okay? So that's what happens when two waves actually interact together. That's going to be our next one. What I would like you to do is go into your textbooks, and I would love for you to answer on page 281. So this should be loaded up onto the G drive for you. Hopefully you've downloaded it. On page 281, there's question 17 and question 18. And I'd really like you to complete both of those. So question 17 is more on the stuff that we were doing last week. 18 is based on this one today. Okay. All right, brilliant. Finish that off and I'll upload the next video for you tomorrow. Thanks, guys.